a system of equations or matrix equation, ax equals b, that's inconsistent. That means that there are no solutions, right? There is no x that can make ax equal to b. So instead, we're going to search for an x hat that makes ax hat as close to what as possible? B. B. So there is no ax that equals b, right? So we're looking for an x that gets us as close to b as possible. If you didn't write b, you got it wrong. Nope. So give him half. Give him half. That is, so if ax hat is going to be as close to b as possible in terms of distance, which that's what these double bars mean, the distance, right? B minus ax hat would have to be less than or equal to, bigger than or equal to b minus ax for every other x in Rn, less than or equal to. It is just less than, yeah. But then Topher gave me a hard time, so I put the equal tos. It is strictly just less than. Okay, and then the equation A transpose AX equals A transpose B, what is that called? The normal equation. No, it's the normal equations. Okay, so today we're going to learn how to find the best approximate solution to an inconsistent linear system. So much of this course dealt with solving a matrix equation AX equals B. However, we saw that such a system is sometimes inconsistent, meaning it has no solutions. But when a solution is demanded and none exists, the best we can do is find an x that makes AX as close as possible to B. Okay, think of AX as an approximation to B, and the smaller the distance between B and AX, the better the approximation. And the distance from B to AX is called the least squares error of the approximation. So the general least squares problem is to find an x that makes B minus AX as small as possible, the distance from B to AX. And we call such an x a least squares solution, and we denote it x hat. So here's the official definition of a least squares solution. If A is an m by n matrix, B is an Rm, a least squares solution to AX equals B is an x hat in Rn, such that the distance from B to AX hat is always less than the distance from B to AX for every x in Rn. So remember, no matter what x we choose, AX is going to be in the column space of A, because A times x is just going to create a linear combination of the columns of A. So x is a vector of weights that makes a linear combination of the columns of A. So no matter what x we pick, AX is in the column space of A. So here's a picture where the column space of A is being represented as a plane. And we're going to seek an x that makes AX as the closest point in column A to B. Right, so here's my B. Right, it's not in the column space, which means that there is no solution to AX equals B. Right, if it was in the column space, we would have a solution, we'd be all set. We wouldn't have to worry about this. But B is not in the column space, so instead, I'm trying to find the point in the column space that's as close to B as possible. And we've been working on finding the point that's as close to a point outside of a subspace as possible for the past couple of classes. It's just that we were calling the space W, right? And now we're calling it the column space of A. So the closest point B in col A, closest point to B in col A is called B hat. It's the projection of B onto the subspace col A. So this is what we kind of talked about last class, how to find the closest point to a subspace. And it's just the projection B hat, which remember we found it was like B dot with U over U dot U times U. And the U's were an orthogonal basis for the column space. All right, so B hat is the point in col A closest to B. So instead of solving the equation AX equals B, we're going to try to solve the equation AX equals B hat. Right? B hat is the closest thing to B I could actually solve. And finding B hat is a little tricky because our formula that we learned last class requires an orthogonal basis for the column space, which is only tricky unless if the columns of A happen to already be orthogonal, then we can do it. It's really easy. But if they're not, then a little bit of algebraic manipulation reveals that we could solve this easier equivalent equation. Instead of solving AX equals B hat, we could solve A transpose AX equals A transpose B. And the algebraic reasoning for that equation is in your text. And I hope you read it sometime, but I'm not going to go over it. Okay, so that matrix equation represents a system of equations that are called the normal equations. And a solution to the normal equations is denoted x hat. It's the x hat that is the least squares solution to AX equals B. All right, so ideally we'd like to solve this equation if the columns of A are orthogonal to each other, then we can just do this, right? We could just come up with a B hat and solve this. If not, you solve the normal equations. All right, and then last thing is we have this theorem. If A is an m by n matrix, all of these statements are logically equivalent, which means they are either all true or all false. So if you're asked about one of them, you can answer whichever one is easiest, and then you know all of the other ones as well. So the equation AX equals B has a unique least squares solution for each B in Rm, meaning there's a unique x hat. The columns of A are linearly independent. The matrix A transpose A is invertible. When those statements are all true, the least squares solution x hat is given by A transpose A inverse times A transpose B. I typically don't solve things that way, but you can if you want. All right, so we'll do an example, and then you've got a few examples to do on your own. So A is going to be this matrix 1, 2, 1, 1, 1, 1. B is 0, 1, 2. If I were to try to solve it, I wanted to solve the equation AX equals B. It turns out there's no solutions. How would you go about trying to solve the system AX equals B? Make an augmented matrix, A augmented with B. We're going to do what you said in a second. 1, 1, 1, 2, 1, 1, augmented with 0, 1, 2. Row reduce. I had all this written down and I forgot to bring it with me. You got it? Okay. One, 0, 0. That is inconsistent. Why? Yeah, that last row, the last row says 0x1 plus 0x2 equals 1, right? That's impossible. This is an impossible equation, so we know it's inconsistent. Okay, so it's inconsistent. There is no x that can make this equation true. So what we're going to try to find is x hat, the least squares solution, right? That's going to make AX as close as we can make it to B. So to find the least squares solution, we're going to use the normal equation that says A transpose AX equals A transpose B, and we're solving for X. All right, so A transpose is 1, 2, 1, 1, 1, 1. I just took each row of A and made it a column. And I'm going to multiply that by A. 1, 1, 1, 2, 1, 1. So this is A transpose A. Do the multiplication, and this is a 2 by 3. This one is a 3 by 2. So my result is going to be 2 by 2. Yeah. The inner dimensions match, which means I'm allowed to multiply them, and the outer dimensions will be the resulting dimension matrix. So 2 by 2. So first row times first column, I get 3. 1 plus 1 plus 1. First row times second column, I get 4. And then 2, 1, 1 times 1, 1, 1 gives me 4 again. And 2, 1, 1 times 2, 1, 1 is 6. So there's A transpose A. Sorry, yeah, A transpose A is that guy. And then I'll do A transpose B, which is 1, 2, 1, 1, 1, 1. That's A transpose. B is 0, 1, 2. So I multiply them, and this is 2 by 3. This is 3 by 1. So my resulting 2 by 1. It's going to be a vector with 2 entries. So 1, 1, 1 times 0, 1, 2 is 3. 2, 1, 1 times 0, 1, 2 is 3. So this is A transpose B. So I have to solve A transpose A x equals A transpose B. A transpose A is this 2 by 2. So I have to solve 3, 4, 4, 6 times some unknown x, x1, x2, equals A transpose B, which is 3, 3. A transpose A times x equals A transpose B. How do you solve that thing? Row reduce the augmented matrix. Sorry, I thought I had given you tons of room. So when I row reduce the augmented matrix, let's see, 3, 4, 4, 6, augmented with 3, 3. Okay, so that means that my x hat that I've been looking for is 3, negative 1.5. That's the vector that makes AX as close as possible to B. So I should write down the answer somewhere. I'll write it here. X hat is 3, negative 1.5. So there's my solution. Good question. How close is it? So we're going to calculate AX hat. So A was 1, 1, 1, 2, 1, 1. And I'm going to multiply that by my X hat that I just found, 3, 1.5. And this is 3 by 2 times 2 by 1. I'm going to get a 3 by 1 vector. That's 3 plus 3 is 6. 3 plus 1.5 is 4.5. 4.5. Is that right? Is that my actual vector A? 2, 1, 1, 1, 2, 1, 1. Yeah. So there's my AX hat. Yep, there's my AX hat. Yeah, so the magnitude of that will be, of that minus B, will tell me how far I am from B. But before I do that, I want to write B as the sum of a vector in col A and a vector orthogonal to col A. Right. So that means I'm looking for B hat, right? So this is like what we did last class. We said, I asked you to do this kind of thing many times, except instead of col A, I wrote W. Right? So that means I'm trying to write B as B hat plus Z. So remember that from last class. And B hat, go back to my pictures up here. B hat is AX hat, right? Because AX hat is as close as you can get to B, but in the column space. So AX hat, I just calculated in the previous part of the question. So B hat is going to be AX hat. Yeah. Oh, that's why those numbers didn't look right. Thank you. hold on one second. 3 minus 3 is 0. And then 1.5, 1.5. Yeah, that looks better. That seems familiar. Okay, so B hat is 0, 1.5, 1.5. All right, what were you asking, Iris, about U? Over U dot U times U. Yeah, so that's how we were calculating B hat last class. In order to use that method, U1 and U2 have to represent an orthogonal basis for the vector space, but we don't have one of those for col A. We don't have an orthogonal basis. So we had to come up with B hat a different way. And we did that using the normal equations. And it's actually AX hat. So, and then B is the vector 0, 1, 2, right? And we've got B hat, which is AX hat. So that means, what does Z have to be? 0 plus what gives you 0? 0. 1.5 plus what gives you 1? Negative 0.5. And 1.5 plus what gives you 2? 0.5. Okay, so I've written B as B hat plus Z. They definitely add to B. Are they orthogonal to each other? If you take the dot product of B hat and Z, you do get 0. Yeah, so you should do a quick. I was figuring out what to put in Z to make it so that when I add it to B hat, I get the vector B. So I asked myself, 0 plus what gives me the 0 in the B vector? 1.5 plus what gives me 1 from the B vector? I could put it in a matrix, or I could just say Z is B minus B hat. That's how we did it last class. I was just figuring out what to put in these spots so that these two vectors actually add up to B. And they are orthogonal. If you dot product them, 0 times 0 is 0, and then the second entries and the third entries are the same but opposites. So when you add them, you get 0. Yeah, B hat and Z. B hat dot Z should always give you 0, right? Because they are supposed to be orthogonal to each other. All right, now Z is the difference between B and B hat, right? Z is the difference between B and B hat. So if I want to know how far B is from B hat, I just take the length of Z. That's what I'm doing in this next part. So by definition, a least squares solution, X hat, is the vector that makes AX closest to B. So the distance from B to AX hat has to be less than or equal to the distance from B to AX for every other X. Okay. So I want to compute the distance from B to AX hat. Well, B minus AX hat, we already calculated, is Z. Oops. Right, so Z is 0, negative 1/2, 1/2. So I want the length of this vector. Right, and the magnitude of a vector is the square root of the entries squared, added up. 0 squared plus negative 0.5 squared plus 0.5 squared. I want the length of B minus AX. This is equal to the length of Z. Because AX hat is B hat, they're the same. B minus B hat gives Z. We could also just write it out, right? So this says I want the length of B minus AX hat. B is 0, 1, 2. AX hat was, somebody have it in front of them? Zero, 1.5, 1.5. So that's the length of the vector I want. I do the subtraction, you get Z, 0, negative 1/2, 1/2. This is B, this is AX hat, which is the same thing as B hat, yeah. AX hat and B hat are the same. All right, so a half plus a half squared is a fourth plus a fourth. So the square root of a fourth is 1 over root 2. Right, which is 1 over root 2. Yeah, sorry. So we calculated AX hat in part C. A is a 3 by 2. Multiply it by X hat, which is a 2 by 1, and you should get a 3 by 1. 0, 1.5, 1.5 is AX hat, which is the same thing as B hat. All right, so pick any X in Rn other than X hat. So X hat, remember, was 3, negative 1.5. So give me any X in R2, except that one. R2. 2, 5. Okay, 2, 5. 2, 5. Any random X other than X hat. And I want to compute the distance from B to AX using this X I just picked. All right, so I got to multiply AX. So this is 111 times 211, 111, 211 times X, which is 25. All right, so I get 2 plus 10 is 12. 2 plus 5 is 7, 7. So there's AX. All right, so then B minus AX is 0, 1, 2 minus 12, 7, 7 is negative 12, negative 6, negative 5. And then I want the length of that vector. The length of B minus AX is the square root of 144 plus 36 plus 25, 205, radical 205. Yeah, which one is smaller, 1 over root 2 or the square root of 205? 1 over root 2. The distance from B to AX hat, 1 over root 2, is definitely less than the square root of 205. And no matter what X you chose here, you would get that 1 over root 2 is smaller. Okay, because X hat is the X that makes AX hat closest to B. If it's not, then you messed up, yeah. Okay, so if the columns of A are orthogonal, I could use all the methods from 6.3, where I could find the B hat, which is the same as AX hat, using the orthogonal projection, but only if the columns of A are orthogonal. So I have to check that. So I've got 1, 1, 1 dotted with 2, 1, 1, and I get 2, 3, 4, right? Not 0. So they're not orthogonal. I can't use the methods of 6.3, so you just ignore the rest of this question. There will be one where you go through the rest of this question in your activities, but not for this particular problem.